we were studying linear maps together with bases, and I want to give the last example of this section. Which is known as Hermite interpolation. Interpolation problems are usually it's about finding polynomials with some conditions, and also it involves the construction of such polynomials. So, one of such problem was Lagrange interpolation and Newton interpolation. Both were methods to construct polynomials where at given distinct points it has a given prescribed values, and we wanted to construct polynomials, unique polynomials with some bound on the degree. So, this is more finer than that. So, let me just state the problem first. So, the problem is, if you have r distinct elements in the field K, K double line is, remember our notation, this is either R or C, complex numbers or real numbers, and assume that these be pairwise distinct numbers, and also let us take corresponding to A1 there is N1 into NR, these are non-zero natural numbers, and let us call M to be the summation of this N1 to NR. Now, what do we want to do? We want to construct a polynomial of degree smaller than m, such that the values of this polynomial at A1 is 0 of this polynomial of multiplicity n1, A2 is 0 of multiplicity n2, and AR is 0 of multiplicity nr. So, we are looking for polynomials and the degree should be bounded by this m. So, that means we consider the map is from the set of polynomials with coefficients in K, degree at most n, So, these are all polynomials of degree of these polynomials is strictly less than m. So, this is, we know this is m dimensional K vector space. On the other hand, because m is n1 plus n2 plus nr, we have also this k power n1, this is a vector space of dimension n1. If I take a product with that, k power n2 etc., k power nr, this is vector space of dimension n1, this is of n2, this is of nr, altogether this will be vector space of dimension n1 plus n2 plus nr, which we are calling it m. So, both these are vector spaces of the same dimension, and there is a natural map here. The map is, I will write the map here, take any polynomial g is of degree smaller than m, and map these two. Now, we have to map it to big tuple, that will be blocks, n1 block, n2 block, so on, nr block. Here in the first block you write, evaluate g at A1, then the next is evaluate g prime at n1, A1, g prime is the derivative of g, and so on, go on till g power n1 minus 1 evaluated at A1, and the last block will be G evaluated at AR, G prime evaluated at AR, and so on. The last here will be G power NR minus 1 evaluated at AR. These are the derivatives of G, and then we are evaluating derivative at the points A1 to AR. So, I am going to use this map. So, we have checked that both are vector spaces of dimension m. The map I have defined is clearly, obviously, the map we have defined is k-linear. That is obvious because derivatives, second derivatives, etc., this is k-linear. Now, I want to prove that this map is bijective. So, I want to give some name to this map. Let us give a name to this map, capital phi. So, obviously, the map phi is, we have defined is k-linear. Now, we want to prove that phi is bijective. So, that means given any tuple of blocks, it will come from a polynomial. That means, so this will serve, this will answer our question, namely given then, so if this, then if I have given B1, Bn1, then C1, this is 1. C1, Cn2 and etc. You given such a tuple in Kn1 cross Kn2 cross Knr, then this will come from some polynomial. That means what? That means this polynomial G, when I evaluate it at A1 I get B1, when I evaluate its derivative at A1 I will get B2, etc. When I evaluate this derivative at n1 minus 1 at A1 I will get Bn1, and similarly for the next blocks. And not only that, the polynomial will be unique because this map is bijective. So, therefore, what we need to prove that is the map is bijective. To prove the map is bijective, because both the vector space is k-linear and both the vector spaces have the same dimension, it is enough to prove that either phi is injective or phi is surjective. Obviously, in this case I will choose to prove that phi is injective because it is easier than proving phi is surjective. Surjectivity of phi is in fact the problem of interpolation. So, we will prove that phi is injective. That means, what we have to prove? If phi of some polynomial is 0, then G should be 0 polynomial. So, to prove this, injectivity is equivalent to proving the kernel of phi is the 0 subspace. That means, if somebody is in the kernel, it should be 0, and remember here degree G is strictly smaller than m. So, let us prove this. So, what we have given? We have given that phi of g is 0, but by definition of phi of g, this is g at A1, g prime at A1, so on till g n1 minus 1th derivative evaluated at A1 and so on. This is 0, this is 0, these are all 0. Because the tuple is 0, then each component is 0. But this block, whole block is 0 means derivative of g, derivative of n1 minus 1th derivative of g A1 is 0 and earlier derivative is also 0. That is equivalent to saying that t minus A1, t minus A1 is a factor of g, that is clear from the first component because g evaluated at A1 is 0, but the derivative is 0 will mean the square will also be factor. N1 minus 1th derivative is 0 means this power n1 is a factor of g factor. I am going to write some more. The second block is 0 means same argument, t minus A1 power n2 is a factor of g, because these are different, not A2, A2. These are different, A1 and A2 are different. So, these factors are co-prime. So, if this divides, then product also divides and so on. So, this t minus AR power NR, this is also factor of this, and this factor is co-prime to the other factors. So, that means the product divides that, and maybe something still left, let us call that as a polynomial q with q some polynomial in T. But because the degree of g is strictly smaller than m, and this is the degree of the left hand side, but on the other hand degree of the right hand side is RHS is definitely bigger equal to n1 plus nr, which is m. So, the only possibility is g is a 0 polynomial. So, that implies g must be 0. So, that proves the fact that this map is injective and therefore bijective, and therefore we get what we want. So, this proof is an existential proof. However, if one want to explicitly construct G in terms of these given numbers A1 to AR, then it requires a different argument, which I will not give here, because this example was to illustrate how do we use so called pigeonhole principle in linear algebra. Okay. So now with this I also want to now continue investigation of linear maps between two finite dimensional vector spaces, and for this very easy or very trivial but very important theorem which one keep using again and again is so called rank theorem. So, the rank theorem. This is really trivial theorem, as you will see from the proof, but on the other hand it is also very important theorem. So, this is in fact the beginning of the investigation for the linear maps between two finite dimensional vector spaces. So, let start with the linear map, let f from V to W be a k-linear map, and I only need to assume V is finite dimensional with V finite dimensional. And as you have seen in earlier lectures that the two important subspaces we have attached to this linear map. One is the kernel and the other is the image. So, two important subspaces. Associated to F are, one is the kernel of F, which is a subspace of V, and the other which is image of F, which is by definition F of V, and we have seen this is a subspace of W. And note that if V is finite dimensional, that is what we are assuming, then kernel F is also finite dimensional, because it is a subspace of a finite dimensional. And image is generated by a basis of F, a basis of V, and V has a finite basis because V is finite dimensional. So, image F is also finite dimensional, because image F has a finite generating system. I will write in here in the bracket, since F of V1, F of Vn is a finite generating system for image, where V1 to Vn is a k basis of V. We have checked in earlier lectures, if somebody is a generating system, then image of that generating system is a generating system of a image space. So, both these are finite dimensional. Now, the rank theorem concerns the relation between the dimension of kernel, dimension of the image, and dimension of V. So, then what we want to prove is dimension of V equal to dimension of the kernel plus dimension of the image. This is what the rank theorem is. Very nice important formula which is used very often. So, let us prove this. Proof is, as you will see, it is almost trivial. So, proof. We know kernel is a finite dimensional subspace. So, I can always choose a kernel, a basis for the kernel. So, let let U1 to UR in the kernel F be a basis, be a k basis of kernel F. And we have learned that whenever you have a basis of a subspace, we can always extend to a basis of a bigger space. So, and extend U1 to UR by adding some more elements. Let me call the extra elements to be V1 to Vs. I have added extra vectors. I have extended this. This is a k basis of V. Now, what is the images under F? When I apply F to U1, so applying F to this basis of V, F of U1 is 0, this will happen till F of UR, these are all 0, and then F of V1, F of Vs. Obviously, then this is a generating system for the image. because this is a basis of a image and these guys are 0. So, only this will contribute. So, this is a basis of the image. Now, if I prove that this is a generating system. If I prove that this is a basis, then I would know what is the dimension of the image space. I also know dimension of the kernel space, and then this. So, first note that f of V1 to f of Vs is a k basis of the image. So, to check that one will have to check that these are linearly independent, because it is already a generating system, and if I check that it is linearly independent, then by definition it will be a basis. So, if A1 f of V1 plus As f of Vs, this is 0, then we want to conclude that all these A's are 0. But because f is linear, this is nothing but f of A1 V1 plus f of As Vs, this f of this is 0, but that will mean that this combination A1 V1 plus As Vs belong to the kernel, but kernel has a basis U1 to UR. That means this we can write it as combinations from the U1 to UR. So, that is B1 U1 plus BR UR for B1 to BR scalars. But then this will give us if this should imply that all A's and all B's are 0, otherwise it will be a contradiction to the fact that U1 to UR together with V1 to Vs is a basis. So, that should imply all the A's are 0 and all the B's are also 0. So, we have proved that they are linearly independent. So, we have proved that this image space is a basis, but then look at the formula what we wanted to prove, dimension of V, because U1 to UR V1 to Vs is a basis and any two bases have the same number of cardinality. Therefore, this dimension is R plus S. But R is the dimension of the kernel and S is the dimension of the image. So, that proves our theorem. So, it is really very easy theorem, but soon I will show you by example. It is very important to know this theorem. Okay. So, before I go on, I just want to introduce here a definition. If F is a linear map from V to W, K linear map, then the dimension dim K image F, this is called the rank of F, denoted by rank Kf. Note that this dimension could be infinite also, but definitely it is finite when V is finite dimensional. So, if V is finite dimensional, then rank of F is finite. That means it is a natural number. Similarly, some people also call the dimension of the kernel. Kernel is also called null space. Null space of F. And with that also some people call dimension of the kernel as nullity, and that is also finite. It is a natural number n if V is finite dimensional. So, the rank theorem simply says dimension of, if V is finite dimensional, then dimension of V equal to nullity of F. This is nullity of F plus rank of F. So, it is also sometimes known as rank nullity theorem. I will not use this terminology, I will stick to what rank theorem. Okay, fine. So, in other words also, so the same statement one can also write it as rank F is also codimension of the null space in V. Recall that, remember, if U is a subspace of V, K subspace, then codimension of U in V, this is by definition dimension V minus dimension U. Definitely this is bigger equal to 0 because U is a subspace. Codimension is always bigger equal to 0. Sometimes it may happen that V may not be finite dimensional, but codimension of U could be finite dimensional. Let us look at the example. So, example, for example, if you take V any k vector space and you take basis, choose a basis with basis Vi, I is arbitrary index set. So, now you fix a subset, fix J, a subset of I, J finite subset, and omit J from I. So, that means you consider the family Vj, Vi, I varies now in I, but not in J. So, only finitely many basis elements are not here in this family, namely those which are indexed by J, and let U be a subspace generated by these Vi's, K Vi as I varies in I minus J. Then obviously this family Vi, I varies in I minus J is obviously linearly independent and it is a generating system for U. So, this family is a K basis of U. So, if you look at dimension V minus dimension W, it is extra elements needed are J. So, therefore, in this case codim Ku V, this is nothing but the cardinality of J. This is nothing but the cardinality of J. So, this is one way to produce arbitrary codimensional subspaces. this I will come back to this study systematically in the section called quotient spaces. Okay, so I want to consider some examples which will illustrate the use of rank theorem. So, first example, this is we have proved earlier also, but once again we prove by using rank theorem. This is dimension formula. Which say that if let U and W be two finite dimensional subspaces of V, K subspaces of V, then remember the dimension formula says that dimension of the sum space, dimension K of U plus W plus dimension of U intersection W equal to dimension of U plus dimension of W. We have proved this much earlier, but this time I want to give a proof by using rank theorem. And before I give a proof, I also want to say that this is the analog of principle of inclusion exclusion from set theory. You know, principle of inclusion exclusion is the cardinality, dimension is replaced by the cardinality. But before I give a formal proof, I would like to take a break and then we will continue after the break.